So under the fluid mechanics, we already covered the thermophysical properties. Some of them, right? So we covered the density, rho. We covered the specific weight, gamma, right? Which is equal rho times the gravity acceleration. We covered the specific gravity, which is Sg, which is the ratio of the density of the fluid to the density of water at 4 degrees. Excuse me. Then we covered also the specific volume, which is V small, which is the inverse of the fluid density, right? So if you look to these thermophysical properties here, it gives you the sensation that, remember, keep in mind that rho is mass over volume. So mass is included in all of these properties. So these thermophysical property, it's measure the heaviness of the fluid. So these are all indication about how heavy or light the fluid. It measures heaviness of the fluid. But there is another property that's very important that actually tells us about fluidity. When I say fluidity, it means that how easy or hard the fluid can flow, right? So it gives me an indication about the flow resistance, right? So for example, we know that gases can easy to flow, right? The next one would be, for example, I pick up water, right? Then next one, I would say oil. And we all know that how hard honey can actually transport, right? Or can transfer, can flow, right? So what is the thermophysical property that give us the indication how easy or hard the fluid can move? This is what we call it actually the dynamic viscosity. And dynamic viscosity takes the symbol mu. That's the dynamic viscosity. Let's look to the, I'm just arranging my paper here. So dynamic viscosity okay. So the dynamic viscosity actually is measured by unit called Pascal second, right? So the units is or Pascal second, and we all know that Pascal is the unit of pressure. So if you want to break it down a little bit, it's going to be Newton per meter square, and we all know that Newton is mass times acceleration, so it's kilogram meter per second square. So if I want to break down that unit, it's going to be kilogram meter per second square. That's just equivalent for Newton. I still have 1 over meter square here, then I still have the second in here, right? So if you simplify that, it's going to be kilogram per meter second. So either it's Pascal second or kilogram per meter second. One other unit that we use for the dynamic viscosity, it's the 1 Pascal second is actually equal 10 poise. So poise is another unit that we use a lot for the viscosity. So either this one or this one, they are related by 10 times. So 1 Pascal second is simply 10 poise. That's the dynamic viscosity. The second type of viscosity, we call that the kinematic viscosity. And we give the symbol of nu, large nu, capital nu. And the kinematic viscosity is simply the dynamic viscosity divided by the density. That's a definition of the kinematic viscosity. So we relate the fluidity to the heaviness of that fluid, right? So if I want to look to the unit, I'm going to use a breaking down unit here. So it's kilogram meter per second, and density is kilogram per meter cube. you will find that the final unit of the kinematic viscosity is actually meters square per second. We know that meter per second square is acceleration, meter square per second is the kinematic viscosity. We use also another unit for the kinematic viscosity. We call that actually the stock, and the one stock is actually 10 to the minus 4 meter square per second. So that's another unit. You find that in the fluid mechanics book all the time. So that's just an introduction about the viscosity. Again, why we study viscosity? Because, for example, if you are a thermal hydraulics engineer, if you're a hydraulic engineer, and you would like to select a pump to drive liquid from one location, from like the desalination station to living area, or you are designing a piping line in power plant, you are designing a pipeline to transport milk in a dairy product factory, the viscosity is a crucial property that you need to know because it's going to determine, for example, the power, the pressure, the flow rate that's required to drive that liquid into the pipe. That's why it's involved more in selecting equipment used in fluid mechanics. That's the importance of the viscosity. So let's now imagine. Let's imagine that there's one plate and a second plate at the top. And let's imagine that between the two plates, we're having water. And I'm going to express the water as, let me use a different color here, as layers. So, okay, this is like my water here. There is one layer in touch with the lower plate. And I will keep adding layers until I get the top layer that's in touch with the outer plate. Okay, the lower plate is fixed. It's not moving, but we will move the upper plate. So then let me mark a line of molecules selectively here. Then what I'm going to do, I'm going to mark that location. I'm going to call this molecule is at distance y. Let's measure from here. Then I'm going to pick another molecule that's a little bit apart, far away. I'm going to call this is measured from the same reference line to be at distance y plus dy. Okay. Then I decided to pull out that plate with velocity u. Pull it out. What's going to happen? When you pull out that plate with a certain velocity, the layer of the fluid that's intact with the upper plate will start moving. Then the interaction between the first layer and second layer will allow the first layer to drag the second one with another motion. And you keep doing that all the time, except the layer at the bottom of the fluid, which is intact with the stationary plate, will not move. So after a few seconds, a short period of time, you'll find this molecule maybe came up here, this one maybe came up here, this is maybe came up here, this is maybe came up here, and this will go the further one out of them. So we end up having something like this. And if that space is very narrow, very small distance, we always assume the variation, the distribution is linear. Keep that in mind. For a short or narrow spacing between the two plates, you can assume the velocity will change linearly in between these two plates. Okay. Now let's go and find the two molecules. This molecule became here, and this one became here. So I got that shape here. Let me isolate that shape actually here and scale it up so we can see a better view of it. So this is the first molecule. It moved up to here, and the upper molecule moved up to here. Remember, distance was measured to a reference line. This is y. This is actually measured y plus dy. So the height of this shape here is dy. Now, since I pulled everything for a constant period of time, let's assume that we pulled it for dt. So I want to know what this distance is. This distance, it's going to be tied to the velocity, right? So we will assume that this plate this layer, that molecule was moving with velocity u, but I know the molecule at the top is moving with higher velocity value because the velocity decreases as we go down. So I'm going to call that molecule was moving by u plus du velocity. So if I want to get that distance here, we know that velocity is equal distance over time. So this is actually, okay, velocity is distance over time. So if I want to get the distance, I should multiply velocity times the time. So the velocity here is u, so this is u dt. This will give me the distance. The other one will be u plus du times dt, right? Let's break this into two shapes. So the line of molecules here moved equally up to this level, then start to see a difference in the motion of the molecules. And we call this angle actually d theta. And we call that shape is a deformation of the fluid. So this is, you remember the original definition of the fluid, it's substances that can be deformed continuously. That's the deformation here. So that's very important to come with a good relationship between velocity and the deformation here. So again, we break down that shape into two parts, and this one is showing the deformation here. Now let's get tan theta, or tan d theta. Tan the angle, I'm going to get that distance divided by that distance. This distance is the difference between the long and the short lines here. So I'm going to get u plus du times dt minus u dt. So I end up having, let me write it down, u plus du times dt minus u dt divided by the distance, which is y plus dy minus y, right? So if you do that, you will find that tan d theta will simply equal du dt divided by dy, okay? If that theta or d theta is super tiny, super small, we took a fraction. So for small deformation, tan d theta can be assumed to equal d theta. So if I substitute here, I will have d theta equal du dt divided by dy. I will divide both sides by dt, so d theta by dt will equal du by dy. The rate of the angular deformation is equal to the velocity gradient. Velocity gradient, and this is the rate of angular deformation. Okay, this is very important relationship here. So now, remember, you are dragging these layers by a force, and this force, because you drag the velocity, and the velocity will drag all the fluid layers. So there is a force, there is a hidden force that's gonna pull out these layers and move that way. And this force is applied parallel to the layer of the fluid, so that's causing actually shear. So the shear stress tau, again, go back to the general definition of the fluid. Its substances can be deformed continuously under the action of shear force of any magnitude, right? So now there is a shear force applied to an area, and the force is parallel to the area, so that's what we call the shear stress, right? So the shear stress is proportional to the angular deformation, d theta by dt. So I would say that tau is also proportional to the velocity gradient. If I want to remove the proportionality sign, I have to put constant. So this is equal to constant du by dy, and the selected constant is actually the dynamic viscosity here. And we're going to actually highlight this equation or that relationship, and this is called Newton's law of viscosity. And this is very important fluid dynamics relationship. So the shear stress applied to the fluid to cause deformation is equal to viscosity. It makes very sense. Viscosity has to be included into the motion the velocity gradient of that fluid material, because it's indication of the resistivity of that fluid to move in all the time. So that's Newton's law of viscosity. So if you give it a more focus here, again, I'm going to write it down here. So the shear stress equal to mu du by dy. So if I want to plot a relationship between the y-axis presenting tau and the x-axis is du by dy. So remember, this is like z equal a w. So this is linear relationship, right? So this will be a line that passing by the origin, right? So I'm going to have a line like this. And what's your expectation for the slope of that line? The slope is presenting the viscosity, right? So this is maybe air. This is maybe water. This is maybe cold water. This could potentially be like oil, and this could be like honey. We know that viscosity is increasing for these liquids, right? And which means that slope has to go up. So this direction is indication the increase of the viscosity of that fluid. Okay. All fluids that follow this relationship or follow Newton's law of viscosity, we call them Newtonian fluid. So again, if you can plot this again, tau versus du by dy, you will find that here is a linear relationship. All fluids behaving over that line, we call them Newtonian fluids, which mean that they can satisfy this relationship up here. And you will find like quicksand is behaving like this. Quicksand is a solution of water and sand used for a specific application. Polymers are behaving like this. Then there is some other advanced polymers like plastics. It's behaving like this. You'll find that viscosity has a constant value plus mu du by dy. So if I want to write the relationship for this, tau is equal a, which is this distance here, right? Plus mu du by dy. So this is the model that describes the motion of the plastic material, and so on. I hope that's give you guys a sensation about the importance of viscosity. And it's clear from this graph, when I put air, water, cold water, what you can get out of this. It seems to be that viscosity is changing relative to the temperature, right? It's very rarely to change with pressure until you go for huge pressure difference, but it's mainly affected by pressure. We all know that if you have a honey in a jar and it's frozen, you cannot flow it down. Simply, you make a warm water path for it. You put the jar in, and it's after a few minutes, it's gonna start move easily, right? So which means that increasing temperature will reduce your viscosity. This is mainly for liquids, guys. And the opposite for the gases. So as the temperature go up, viscosity increase for gases. Why is that? You increase the temperature. Remember, gases already, they have a strong bond force or bonding force, right, between the molecules. So when you do increase the temperature, you weakness that bond. But this bond is already weak in the gases, right? So what happens when you increase the temperature, you actually increase the kinetic energy of the molecules, and you start moving very, very fast, right? Now you are actually allow them to be more closer to each other because of that high speed, right? So you actually shrinking the intermolecular spacing between the molecules, which means that with that random motion of these molecules at high energy, it makes the flow of the gases actually less easy, right? Again, the change is very slight, but we have to mention that temperature increase results in increasing viscosity for the gases. So that's conclude the viscosity. There is a handout, actually, I'm gonna upload that into Moodle as well. It's just like reviewing the concept again. So for example, when I say here, force equal shear stress times A, right? So the shearing force, you remember shear force is the force over the area, and they are parallel. So I can get the force by multiplying the shear stress times A. So the shearing force, F, is equal to the shearing stress, right, times the surface area. correct? Do you remember when we have that narrow spacing between the two plates and we presented the fluid with layers, right? The concept said here, the dash principle, fluid molecules next to the solid surface move with the solid surface. So if you have a molecules that attach it to the stationary surface, it will not move, right? And the molecules that attach it to the moving surface, it will move by the same velocity, right? What we call that, actually, we call that the non-slip condition. Non-slip condition, okay? So, non-slip condition. Non-slip condition means that molecules attached to the wall will take the same velocity. If the wall is stationary, velocity will be 0. If the wall is moving, it will take the same velocity. Then whatever in between will be distributed either linearly, if we are talking about narrow spacing here, or some way, different some way. For small distances, a fluid between two plates will have a linear velocity profile. Therefore, the rate of change in velocity per height is equal to, this is what we got. So if it's linear, du by dy can be simply approximated by delta u over delta y. So u at the upper plate minus u at the lower plate divided by y of the upper plate minus y of the lower plate. Keep that in mind because we're going to need that for the homework problem. Mu is defined by the dynamic viscosity, right? Keep in mind, it's dynamic viscosity, not the kinematic one. For gases, resistance to shearing is largely due to, we're going to talk about this later on, but this is about the momentum transfer. As you know, guys, molecules has mass. It's moving by a velocity. And we multiply the mass times velocity is simply the momentum, right? You already guys took statics and dynamic courses. So when the molecule get energized by the high temperature, right? You give it the temperature, star move from one level to the other. When it moves, it carries momentum with him, right? So it takes momentum. And due to that momentum carried by that energy carried by the molecule, I said this molecule will get closer to another one and increasing the resistance of the fluid to flow, which means that it's getting your viscosity up. When the viscosity goes up, the shearing is becoming resisted. What else? For a liquid, resistance is a function of momentum transfer and cohesive force. So in the gas case, it's only the momentum. In the liquid phase or the liquid case, we also add the bonding force, the cohesive force. This is just a fun exercise here. It's explaining if you have two trains next to each other and someone is standing up on that train and the train is moving with a higher velocity compared to the other one. Then the guy standing up here, he's carrying a basketball. And now he's standing still over that train and the train is moving with velocity v1, which means that the velocity of the guy is also v1 and the velocity of the basketball is still v1, right? Then he decided to throw away the ball to another person standing over the second train that's moving by a slower velocity. What's the expectation for the second train when the guy actually holds that basketball? So you are throwing high energetic basketball to a person who actually possesses lower energy. So you are adding to its energy. So you are expecting that the train velocity would be increased by adding that extra energy to it. So doing this, V1 is expected to decrease. Why? Because it lost energy, right? And V2 is expected to increase because it gained energy, right? So momentum transfer, remember the basketball has a mass, it moves with a velocity, so it's actually a momentum. So momentum transfer from high speed or high velocity body to a lower velocity body should slow the faster one and increase the velocity of the second one. Later on, we're going to talk about momentum transfer and so on. So, but just give you the sensation. Think about these basketballs like the molecules of the fluid moving from one layer to the other, one layer to the other, one layer to the other. This is what's happening on the smaller scale. Okay. Last one, derived dimension unit for dynamic. dynamic viscosity, right? We talked about this. The dynamic viscosity has a unit of Pascal seconds, or it ends up to be, it's hard for me to remember, kilogram per meter second, kilogram per meter second. So as this is a unit, right? So if I want to do the dimension, it's going to be M L minus 1 T minus 1 if I'm using the MLT system. I can redo that again. Pascal is Newton per meter square, and there is seconds. Newton is force. So if I want to do the dimension, it's going to be F L minus 2 T plus 1 if I'm using the FLT dimension system. Okay, so this is just the in-class exercise to review the concept that we covered in the viscosity. Let's do an exercise about the viscosity and the Newton's law of viscosity so we can understand how to apply that equation, right? So the kinematic viscosity, its dynamic viscosity and density occurs often in engineering equation. They have been combined to form the new formula, kinematic viscosity equal dynamic viscosity over the density, right? We talked about the units, right? It's meter square per second. And if you want to do that as a dimension, it's L square T minus 1. And you can do that in the FLT system as well if you need. This is an example here, and this will be close to some of the homework assignments. So this is a tilt plate. There's a fluid moving above that plate. The thickness of the fluid layer is H, okay? And this is how the velocity distribution looks like. So the velocity with no slip condition, showing zero velocity for the first layer. You go a little bit up, it's increasing velocity. You go a little bit up, it's increasing velocity, until almost the velocity is not going to change too much here. So this is what we call the velocity distribution. And you were given an equation for that velocity distribution. The velocity at any position y equal u, which is the outside velocity here, and function of the y and h. Y is the location measured from here, and h is the thickness of this layer. So for example, if you put y equals 0, which is this face here, y equals 0, this term goes away, this term goes away, u is 0, right? If you put y equal h, which is the maximum height here, h over h, that's 1 times 2, that's 2. 2 minus 1 is 1 times u, it's u, so the velocity is going to be u. And anywhere in between, you put any value for y, you get the velocity distribution here. Okay, so let's see what the problem is asking for. Use viscosity of mu. Find the shear stress. I want to get tau, the shear stress, which is equal mu du by dy at different location, at y equal 0, at y equal h over 2, at y equal h. So let's write down the equation. Tau is equal mu du by dy. So you want to take the first derivative as a function of y for this equation here. So it's going to be mu times u, right? Let's take the derivative here. We are differentiating relative to y, right? So it's going to be 2 over h minus, this is y squared, is going to be 2y over, remember this is h squared here. You rearrange the equation, you're going to get actually mu times, I'm going to put the u inside, 2u over h minus 2uy over h squared, whatever. Now, at y equal 0, right? That's the first part. This term goes away, so the shear stress is actually 2u mu over h. At y equal h over 2, you put y equal h over 2, so tau is equal mu 2u over h minus 2u, y is equal h over 2, and this is h squared. This will cancel out, 2 will cancel out. It's 2u over h minus u over h. It's going to be mu u over h, right? Then at y equal h, you're going to put y equal h in this equation, goes away with the square. So tau will be actually mu 2u over h minus, the h will cancel out here. It's 2u over h. So this would be actually 0. That's how we use the velocity distribution equation to calculate the shear stress at different locations. So you need 2 mu u over h at the face. Shear stress. Why the shear stress is decreasing this way? It's almost 0 here, because you don't need really that much force, which can be translated to a shear stress to deform the fluid. It's free. The layer of the fluid here is not affected by anything, right? But the layer of the fluid intact with the solid has a resistance to flow. It needs higher force to pull that layer and shear it and deform it, right? Because it's attached to the wall because of the no-slip condition. And that's explained why the shear stress is maximal at the intact, the layer intact with the solid body, and decrease as you go up, okay? So that's another class hand exercise for practicing things. Next would be the looking for another phenomena. Actually, yeah, let's keep the example. I have another example in viscosity. Let's do it first before we jump into another concept. So this is a real problem. I think it's from the book. As you can see, that this is a rotating disk here. This is the axis of rotation, and this is a solid plate, and the spacing between them is super tiny. We can assume that, and it's filled with oil. So the device below has a disk rotating on a shaft. The gap between the disk and the boundary is small. It's actually mentioned here. Why? And the oil is in the gap. So we would like to calculate if the rotation rate omega is equal to radian per second, what is the speed, the velocity of the oil touching the disk at r equals 3. R is measured from here. So the center line is r equals 0, and it's actually here. So you move away like this, that's increasing r, and that big diameter here is d. I'm going to call that radius is r capital. So part A is asking to calculate the velocity, linear velocity, for a point at 3 centimeters away from the center line, and at y equal to y is measured from here. So this is y equals 0, and the top layer here, this is y equal to 2 millimeters. Okay, so I need a point actually here that's attached to the rotating disk. What's the linear velocity? We know that linear velocity, it's equal to the angular velocity times the radius, right? Angular velocity is given by 2 radian per second. And the radius I need to calculate is 3 centimeters. Actually, it's 3 centimeters. So this will give me actually 6 centimeters per second. You can convert that into 0.06 meter per second if that's something you prefer. So that's the first part. Number 2, if a rotation rate of omega now becomes 1 radian per second, what is the ratio of the shear stress at 2 centimeters to the shear stress at 3 centimeters? Why should be different? Okay, let's see. So you want to mark 2 points. One, let me actually draw this again here. Here is the disk. Remember, we measure r from here. So at this point and at this point, this is r equal 2 centimeters. This is r equal 3 centimeters. And you want to do that, get the ratio at these two distances using omega equal 1. Okay, first, I want to calculate shear stress. What's the shear stress? Tau is equal to mu du by dy. I'm not given the velocity distribution here. Since this spacing is super narrow, is tiny, as given, I can approximate du by dy by the difference in delta u over delta y. I pick 2 points with 2 different velocity. I know what's the y coordinate for them, and I will do it. Remember, the oil is filling that gap here, and y is measured from here, right? So this is y equals 0. This is y equal 2 millimeters. That's the thickness of that layer, okay? So let's get the shear stress at r equal 2 relative to the shear stress at r equal 3. This will be mu delta u by delta y at the position of 2 centimeters divided by mu delta u by delta y at the position of 3 centimeters. So I want to look to the variation of du by dy here. That's at r equal 2, and the variation of du by dy here. So mu will be canceled out, right? So delta u over delta y at the 2 centimeters, I'm going to pick this point and this point, right? So it's u minus u divided by y minus y. So the velocity at 2 minus, we know the velocity here is 0, divided by y of this point is 2 millimeter. I'm going to make that 0.002 minus y of this point is 0. Then you divide that by the delta u by delta y at this location, u minus u, y minus y, divided by y minus y. So it's u at 3 minus the velocity here is 0 minus 0.02 again. This is y of this point minus 0. This will cancel out. So it's going to end up to be u2 over u3. The velocity at this point divided by the velocity at this point. And the velocity is different. That's why the shear stress will be different, right? So tau 2 over tau 3 should equal to omega r of 0.2 divided by omega of r of 0.3. Omega will be canceled out. It's going to be 2 over 3. So the ratio of the shear stress is 2 over 3, right? So the shear stress at point number 2 is 2/3 what you need for shear stress at point number 3. Why? Because the more you go out, centrifugal force is increasing, right? And to change that, it's the shear force will increase and the shear stress will increase, right? We know that if you are holding a stone and you are tightening the stone with a rope or a wire, then you start rotating it. The longer that rope or that wire is, the more force you'll get because the centrifugal force is increasing, okay? So this is answering the part B, okay? Part C is looking for if the dynamic viscosity mu is given by 0.01 Newton second per meter square, what is the shear stress of for the condition at r equal 3, y equal 2, omega equal 2. So I want to calculate the shear stress for the given condition. Mu is given, r is given, 2 is given, the y and omega is equal to. So again, tau at 3, right, is equal mu delta u by delta y at that point number 3, right? So mu is given by 0.01. Delta u, I'm going to pick two different velocity here, right? So it's going to be u minus 0, u at this point minus 0, divided by 0.02 minus 0, right? And the u will be calculated here by omega times r. Omega is given by 2 radian per second, and the r is 3. So this will be omega r over 0.02. Omega is given by 2 radian per second. The radius is 0.03 divided by 0.002. I think I did calculate that number. Oh, I missed the mu, guys. We are missing the mu, right? So there's mu as well, which is 0.01. So 0.01 is mu. Omega r here, that's the velocity divided by that spacing. I got this value to be 0.3 Newton per meter square, right? That's a shear stress. So that's part number C. The last one is a little bit hard. It's asking for a torque. Calculate the torque to rotate the disk if omega is equal 5 radian per second and the diameter is 10. First, how we get the torque, right? We know that from, if you guys recall from the dimension class, we talked about the torque is simply the force times the distance. In this case will be r. This is the r that I need to calculate the, he is asking for the torque, right, for the whole thing. So that's, I would say this is r capital. Keep it r small for now. So torque is equal F times r, force times distance here. Now let's take a projection view for that disk. So this is a big disk. Here is the center line. And we know that everything changes based on where you are from that center line. Everything is function of r. So let's assume that we're going to pick a location here that at radius r. And we cannot just deal with a line, so I'm going to take like a small strip. So the thickness of that strip is simply dr. Can you get me the area of that strip? Because we know that shear stress is force over area. So what I can do, I can say, okay, torque is F times R, but shear stress is force over area. So I can get force from here by multiplying tau times A. Then I can substitute here. So the torque is actually tau A, right, R. So what's the area? Get me the area of that strip. Think as you get a scissor and you cut that strip and make it like rectangular. So the length will be the perimeter, 2 by r, and times the thickness, which is dr. So that's actually, this will give me the area, 2 pi r dr. 2 pi r is perimeter of the circle, and dr is the thickness. Think again, you got a scissor, you cut that one, and you straight it up as rectangular. So to get the actual value of the torque here, since tau is function of f, and it seems to be a also is a function of r, and the force will change with the position. So I need to integrate that from 0 to the r capital, whereas r capital is the outside radius of the disk. So if I want to do that, it's going to be integration from 0 to r. Tau now is going to be mu du by dy, that's tau, times the area, 2 pi r dr, then times r. So that's tau, that's the area, that's the r that came from the torque equation, right? This is linear velocity, and we know that linear velocity is omega times r, so torque can be also integration of 0 to r, mu omega r over delta y, right? Because we can approximate that du by dy by delta u by delta y, times 2 pi r dr times r. Now let's take the constant out. Mu is constant, omega is constant, delta y is constant, 2 pi is constant. So what's going to left here is there is one r, there is a second r, a third r, so this is r cubed dr from 0 to r. Then you integrate that, you're going to end up having mu omega 2 pi over delta y, r to the fourth divided by 4. You have to substitute from 0 to r capital. So you will end up having the torque. It's actually 2 pi omega mu divided by 4 delta y r capital to the power fourth. Omega is given by 5 radian per second. Mu is given by 0.01 in the problem. And delta y is the 2 millimeter. And the radius is given by 10 centimeter. So if you do that, you should get the torque equal to, the value I got, it's 2.5 times 10 to the minus 4 Newton meter. Okay, that's another exercise, how to use a viscosity and the Newton's law of viscosity to solve problems. The last two concepts in this chapter, actually, I would like to share with you guys. The first one is called the compressibility. Imagine that you have a liquid sitting in a tank, and this is the level of the liquid, and the liquid is covered by a gas with a certain pressure P, and the volume of that liquid is V. Then you decided to increase the pressure above that liquid, so you increase that pressure by a value of P plus dP, and that pressure was high enough to push your liquid level from here to here. So now your volume decreased by dV, and the new volume now is becoming V minus dV. So you compressed the liquid by increasing that pressure, okay? This is happening. Maybe we don't see that, we don't feel that for liquids, but we feel it more for gases. But we are trying to generalize the relationship here. So we define something called the bulk modulus. What's bulk modulus? We give that E capital V. So the bulk modulus is, in a simple language, is the differential pressure, dP, that's responsible for shrinking the liquid volume. It's a differential pressure that's needed to reduce the, shrink down the volume of the liquid. And the minus sign here, because of that shrinking, it's dV, the change of the volume is negative because it's going down. So that's the bulk modulus and how we define it. Then we can actually relate that to the density because usually we have the thermophysical properties, right? So what happened is we know that rho is equal mass over the volume, right? So I can get the volume is equal mass over the density, which can be written as mass rho minus 1. You can get dV is equal m. You're going to differentiate that. It's going to be minus rho to the minus 2 d rho, right? So if you divide that by volume, so dV by V, it's going to equal minus m over V. I will take rho minus 2 to the denominator. It becomes rho square d rho, right? This is actually rho is going to go away with this. So I'm going to end up having minus d rho over rho. So dV over V is equal d rho over rho. If you go up here, you can actually rewrite the bulk modulus as minus dP divided by, the minus will go away, so it's going to be plus d rho over rho. So we have two relations for the bulk modulus. One is function of the pressure and volume. The other one is function of pressure and velocity, viscosity. And remember, these both for liquids. So the question is, what about gases? Okay, so liquids, we have these two relationships. What about gases? How we can calculate actually the bulk modulus for the gases? That's very simple because for the gases we did cover the ideal gas formula. So P is equal rho RT, right? So by the way, this has to be done under constant temperature. We cannot variate everything at the same time. So we are fixing the temperature to be able to get the relationship between the pressure and the volume, or the pressure and viscosity. So in this case, if we keep the temperature constant and the R is constant, so I can say that P is equal constant times rho, right? That's a relationship here. Then you can get actually dP, it's equal C d rho, right? Differentiating. You can go all the way and substitute into this equation here. So the bulk modulus is equal to plus dB is C d rho divided by d rho over rho. This will go away, so I'm going to end up having C times rho, and C is RT times rho, and rho RT is the pressure. So actually the bulk modulus for the gases is simply the pressure of the gas. That's another concept that you may experience in the homework assignment. The last one I would like to cover with you guys today is what we call the surface tension. If you look to a bulk fluid, and let's assume that you pick a molecule here. This molecule is surrounded by neighbor molecules, right? From all over, from all directions. And between this molecule and this molecule, there is a bonding force, 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 bonding force, a bonding force. So the net force equals 0. That's why in equilibrium, the molecule is not going to move, right? But if you pick one molecule at the top, it's surrounded by the similar molecules of liquids here, 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 here. This is bonding force, bonding force, bonding force, bonding force, bonding force. But at the top, there are different fluid molecules, gases. Assume this is air, right? Which means that the bonding force here is not the same or not equivalent to the bonding force down there, because they are different fluids. So what's happening is you'll find that the net force for the surface molecules does not equal 0. And that's explained why you see that this molecule at the surface is always like pulled down, because the bonding force here is much higher than the bonding force up. So the net force is taking that molecule down. That's why you get the sensation that the surface of a fluid is like stretched membrane like this. And this is what we call the surface tension. So surface tension is a force per unit length that cause liquid surface acts like elastic membrane. Get a cup of water and go and get a little bit of a milk and take a milk droplet, one milk droplet, and drop it over that surface and try to recognize what's going to happen. The milk droplet will go hit the surface and it's going to jump back up before it goes down. It was pushed away because of that elastic membrane due to the surface tension force. Surface tension force, we always give it the symbol sigma. And since it's a force per unit length, so it's actually Newton per meter as unit. Okay, dimension-wise, it's FL minus 1 if you are using FLT system, or you can break down the force into kilogram, which is M, meter per second square, so it's L T minus 2, L minus 1, L will cancel out, so it's going to be MT minus 2. This is where the MLT dimension system, and this is if you are using the FLT system. So this is the surface tension. This explains for you as well when you see like the mosquito is walking over the water surface. It's using that elastic membrane to walk over. Okay, if you slowly bring like a shaving blade, the metal part, and you slowly put it over the surface in an equal position, not tilt, it can actually hang up over the surface of the water. It's because of the surface tension is holding it. So this is the concept of surface tension. Two applications briefly that we use the surface tension for. If you are, I would say this is the application. If you have a bulk of fluid, then you have a bubble in here. Let's say this is a bubble. So the bubble has inner pressure and has outer pressure. And it may collapse or may survive all the way to the surface. You can recognize that when you actually boil your water, right? It depends on the surface tension properties. So we can actually get the pressure difference. This is the pressure difference between inside and outside. Could be a gas bubble, could be a different liquid droplet, right? So delta P can be calculated by sigma over 2R, whereas R is the radius of the bubble or the other droplet. That's one application. The second application, if you have a container of liquid, then you decided to put a very tiny tube into it, you will find that the liquid will rise into that tiny tube. So we would like to know the height that liquid would actually go. If I zoom in here, you will see that this is a pipe, right? There is a liquid here. This is the diameter. We give that 2 radius, and you'll see that the liquid is going this way, right? And you can actually draw a tangent line here. Remember, this is the tangent to the liquid. This is a solid. You measure this angle theta. If you want to get the height h, the height h can be calculated by 2 sigma cosine theta divided by gamma r. Okay, you can find the derivation of that relation in the book. But I want to highlight here, r is the radius of that tiny tube, gamma is the specific weight of that liquid, right? And theta is called the contact angle. So when you have a water droplet or liquid over a surface, if that's a solid surface, and you put a water droplet over that surface, you may find the water droplet spread like this, or could actually looks like this, or could actually looks like this. So contact angle theta is the angle you measure within the liquid to the contact to the tangent line. So I draw a tangent line, and this is the liquid droplet. This is called the contact angle. It's the net balance force between the liquid, vapor, and solid interfaces. Then this is my theta. This is my theta. Okay? You measure through the liquid. Okay? And then later on, maybe when you get in high-level courses, this angle theta is what classifies the liquid to be hydrophilic, hydrophobic. Hydrophilic means your theta is less than 90 degrees. Hydrophobic means that your theta is greater than 90 degrees. Then if theta is go all the way to 5 degrees, call that super hydrophilic. If theta goes to close to 150, 170 degrees, we call that super hydrophobic. And the hydrophilic and the hydrophobic has a great application from your laundry detergent to remove the stains from your clothes, to the spray that we use to you spray your shoe when you go for hunting and get into the mud, it never gets wet, right? To the shirts that never get dirt, and there's many applications. We enhance microfluidics flow in a microchannel by reducing the friction loss using hydrophilic and hydrophobic surface fabrication, and so on. That's conclude the chapter 1. With that, I will guys release the second homework for you. Okay, see you next class.